Welcome to another screencast. This screencast will focus on redshift and blue shifts in astronomy for Earth science. And a good starting point would be to look at the electromagnetic spectrum on page 14 in your Earth science reference table, which is probably your wallpaper on your phone, this actual page, because I know many of you love the electromagnetic spectrum. You can't get enough of it. So if you look, the way it's set up is your smallest wavelengths are on the left, gamma radiation, and your longest wavelengths like radio waves are on your right. In between ultraviolet and infrared, you have visible light. So all of the visible light, violet, blue, green, yellow, orange, and red, fit in this very, very small area over here. Ultra means above, so ultraviolet above violet. Infra means below. Infrared, below red. So it's below the red. Visible light is infrared. So red would be a longer wavelength than blue and then violet. In astronomy, we talk about blue shifts and red shifts. Why they don't call it violet shifts, I really don't have a good explanation for you on that one. So, sorry to clear my throat, but you know it's allergy season. You know how it is, I'm sure. If we take a look at this Doppler shift, and all these movements are relative to this thing over here, which we'll call the Earth. If it's moving away from us, and we're going to say that this is a galaxy, and it's moving away from us, which, by the way, most galaxies are doing in our universe, because the universe is expanding, then we have a galaxy that's not moving at all, and then we have one that's moving towards us. This is what the absorption spectrum would look like. The black lines representing the absorption of the wavelengths through the galaxy, so that galaxy is absorbing those things. And if the object was standing still, this is what it should look like in terms of its signature. And now if we take a look, if it's moving away, that's called a redshift, and the wavelength would be shifted longer, or towards the red end of the spectrum. And if it was moving towards us, it would get more compressed, and it would be a blue shift, or a shorter wavelength. And if we looked at the electromagnetic spectrum on these two galaxies, we would see that here it is standing still. The actual absorption spectrum got shifted towards the red end of the spectrum. In the case of the galaxy moving towards us, the absorption lines are shifted. It's the same pattern. You can see it's the same exact pattern, same spacing, but it shifts towards the blue end of the spectrum, so that would be known as a blue shift. So red shift, the object's moving away. Blue shift, the object is moving towards us. Most galaxies exhibit a red shift in our universe because the universe is expanding. So, a little question that comes up. Look at the spectral lines of the galaxy at rest. Which set of spectral lines best shows what most galaxies are doing? So this would be if the galaxy was sitting still. And which one of these would give us the right answer? Well, if we look, the first one would be wrong, the second one would be wrong, and the last one would be correct. But the question becomes why? Further examination, we can see the first one, the spectral lines are blue shifted, which would suggest that that galaxy is moving towards us. In the second one, which is right over here, second choice meaning, the spectral lines are randomly shifted, so that doesn't happen. And in here, you could see it's the same pattern, same spacing as at rest, but it's shifted towards the red end of the spectrum, which is what most galaxies are doing because our universe is expanding. And since it's expanding, what is it expanding into? Ponder that for a moment and have a glass of chocolate milk, skim milk in my opinion, but it's up to you. Which galaxy is moving the fastest away? Kind of poor grammar on my part. I should have possibly said which galaxy is moving away the fastest. But I'm an innovator sometimes, and sometimes my innovation occurs in grammar, which is why I go to grammar rodeos often. Usually the star at the grammar rodeo. So why is this one the wrong answer? Well, first off, it's blue shifted. This one is red shifted, right? But this one is more red shifted. So therefore, the more red shift would imply that it's moving away faster. So in a similar way, if you have galaxies moving towards you, whichever one is more blue shifted would be moving faster. So not only can the shift tell us in what direction they're moving, it gives us an idea of relative velocity, relative meaning comparative. So you could compare the velocity of different galaxies based upon their red shifts or blue shifts, in the case that they're moving towards us. So in this case, you could see that this would be at rest. It's not super clear. And the lines are showing you how they shifted. You see how the absorption lines shifted towards the red end of the spectrum? Therefore, this particular object is moving away from the observer. Unshifted absorption lines. And so there would normally be color there. That's why they're called absorption, and the gases in that material absorb that wavelength, and that's why we have a blank line there in the electromagnetic spectrum. And here you could see it's red shifted. You could see it's the same pattern, same spacing. They just shift to the red. This object here is moving away from the observer. And here when it's blue shifted, again, same pattern, but it just shifts to the blue, and that means that object is moving away from the observer. Just another example of a diagram that's supposed to be a human eye. In this case, it's stationary. That gives you your lab electromagnetic spectrum. And then in here, it's coming towards you. It gets more compressed. Therefore, the absorption lines would shift to the blue end. Here, it's moving away. They would shift towards the red end of the spectrum. Just giving you another example of it with a fantastically beautiful drawing. Moving away, elongation. Moving towards you, compression. So you could think of a slinky perhaps, and if the objects move towards you, the slinky gets compressed. If the object moves away from you, the slinky gets elongated. Another way to think about it too is good old Superman. All right, so if Superman's flying towards you, you're going to see the blue of his, I guess that's a unitard, not exactly sure. When he's flying away, you'll see the red cape, which would be the red shift. Okay. What oftentimes comes up too is where we are in our solar system. We live in a spiral galaxy, the Milky Way galaxy. We're on one of the spiral arms. We're 2/3 of the way out from the galactic center. So an overhead view, we would look something like that. That would be our location. A side view, we could be over here. And I said could because it could shift a little bit. It doesn't really much matter which arm or which side view, but that's where we're located in our Milky Way galaxy. All right, just have to be about 2/3 away from the galactic center. We could not live in the center. There's just too much radiation for our life forms. And again, just some other depictions of where we are. So there's the sun. You can see from the side view, and this would approximate where the sun would be. Overhead view in our galaxy, which our galaxy is about 100,000 light years in width. Okay, approximate position of our sun. You could see again we're 2/3 away from the galactic center. Very popular T-shirt people have. Lunch boxes too, making a comeback, I guess, right? The lunchbox. So here's a typical Regents exam about our location in the Milky Way galaxy. Give you a moment to digest this one, and you can see that the answer would be choice C. Choice A, galactic center, would be wrong, and off of one of the spiral arms would be wrong as well. And then here's the little side view one that comes up quite often. And you can see that the answer here would be choice B. An older one you could see in the formatting. This is a really super old question. So which diagram best represents the spectral lines of this element when its light is observed coming from a star that is moving away from Earth? We know that would be a redshift, so the spectral lines would be shifted towards the red end of the spectrum. Cosmic background radiation, that comes up quite often, provides direct evidence for the origin of, and what do you think? You can feel the tension, right? It'd be the universe. Cosmic background radiation from the universe expanding from the Big Bang. Take a moment to read this one. A major piece of scientific evidence supporting this theory is the fact that wavelengths of light from galaxies moving away from Earth in stage 3 are observed to be. So take a look. Let me show you where Earth is right over here. Stage 3, what would those wavelengths be doing? They would be longer than normal, which would be a redshift. So as a quick little summary, Superman, If you saw him flying towards you, you'd see mostly blue shift, and if he was flying away, you would just see the red of his cape, or what would be known as a red shift. Hope you enjoyed the screencast, and good luck. We're all counting on you. We're all counting on you.